Hello all, and welcome to your first virtual lab. My name is Lorraine Clark. I'm going to be your professor this semester. It's going to be a very short semester, and so all of your labs are going to be asynchronous like this. The concept here is that you'll watch these videos. I will be available most days. I'll be available during the lab period for you to ask questions and go through it and make sure you understand the assignments. And so today we're talking about the scientific method. I just want to give you kind of a information about what's happening in the lab and what's expected of you first. So scientific method, a historical overview, and then, conclusions are at the end of the scientific method normally. Well, today often people start with conclusions, get confirmed on Facebook or Twitter, and then throw a hissy fit when provided with new information. So we're going to work on doing the actual scientific method. So again, asynchronous labs. Each week you are going to be completing between 2 and 4 virtual labs. Now that seems like a lot, but well, we're doing a lot in the time frame. I expect to be working on labs almost every day. In a normal face-to-face class, you would be doing your labs every single day. You would be in the lab finishing stuff and completing the actual labs. The virtual labs means that you will have assignments that you are expected to do within 2 to 4 days after you've finished. So just make sure that you are participating in those, or you do lose points. So each lab has a handout or assignment or something else that you must complete by the exam related to that lab. Again, expect to spend up to 6 hours of your own time each week finishing labs. It doesn't get easier or faster without me there, so do make sure that you come and work in the lab hours with me. Even in the background, start doing the lab. You get stuck, you can come to me during the lab period if you're paying attention. Okay. And I will be available on Zoom every lab session to work through problems and help with questions about the handout and even previous labs if you are just catching up on them. Sorry, this is not relevant there. I'll fix that soon. And when answering all of these questions that you will be submitting, remember to use your own words. Sorry, let me move my picture so you can see. Plagiarism or copying someone else's exam or some answer key you found online will result in a 0 for that assignment. You will have 2 synchronous labs. Now, all but 2 of your labs are going to be synchronous, and lab 2 tomorrow, Wednesday, will be the setup for your field experiment. I'll explain this on Tuesday, so hopefully you won't be too confused. But you'll be meeting in the Zoom room during the lab period. It's 10:45 to 12:15. I've shifted it forward just about a half hour. And you're going to be assigned to groups. Probably there's not too many people in this class, so we're all going to work in one group. But I will do a session to work through hypotheses, figure out who's doing what. You guys are all going to be collecting data. And your proposal for that report is due Tuesday, June 7th, and the actual collected data is due June 20th. So all of this information will be explained on Wednesday as well. And June 22nd is the second synchronous lab where we will go through the collected data and analysis. This is all, and I already do have some things set up in Canvas, recordings for you to actually complete this. Okay, simutext. There are online activities that will be completed alongside the in-person labs to practice and reinforce your activities. Now, I'm still setting up the simutext as we speak. I do hope it's set up by Friday. So I'm going to be showing you a different version of it, but it's the same concept. Okay, but information about accessing your simutext labs and class activities is on Canvas in the simutext module. And you will need to sign up and complete the simutext lab by next Monday. And so that's the day before the lab exam is due. Alright, so this is the basics of the scientific methods, which is what we're going to be going through today, and I'll show you how the simutext applies to that. But the idea is that you ask a question. Why does this happen? You state a hypothesis and answer to that question. Conduct an experiment to test the hypothesis, analyze the results, and then hopefully make a conclusion about whether or not you were right. So the first question we want to ask first is, if we want to do the scientific methods, well, what is science? So think about that for a minute. You're in a science class, but what is science? It's a study, it's not really a study actually. Science is derived from the Latin verb to know. It's a way of knowing. There are other ways to know the world. Understanding the world through experience, understanding the world through the lens of morality, philosophy, theology, belief, family, etc. All of those pieces make up different realms of understanding the world around you than science. Again, this is a way of knowing. An approach to understanding the natural world. We will be doing as much as possible to understand the natural world. One of the things I like to emphasize is that this natural world is not that understanding the natural world is not the only way to understand your life and your world. Okay, but science is what we're focusing on in this class. So think like a scientist. You make observations, you form logical testable explanations, and then you test and do an experiment. So all experiments begin with an observation. So let's say you're driving to class. Obviously, you don't have to drive to class. This is a remote class, but all experiments will begin with this observation of try to start your car, and your car won't start. Your car has stopped running. Possible explanations include you ran out of fuel. That's a good explanation. I had a car that had a broken fuel gauge and would always tell me that it was full, so I had to keep very close track how much gas I was using and how much I would fill up the tank with, so know when it was fully filled up. Maybe your battery died, and you may actually be doing actual experiments right now, just all around you. You make small hypotheses and you find small things. For instance, if your battery died on your car, a really quick thing to do is you might say, if my battery died, so my battery died is an explanation, a hypothesis. And you say, well, if my battery died, then how would I test that? Well, I'd say, if my battery died, then my battery would actually have a, then there would be no lights in the car. I would only hear click, click, click. My headlights won't work. So you test those things, you find out that that's true, you need to jump. And this has happened to me before when I've left my car on overnight, or left my headlights on overnight. So what I just did was, so I have a hypothesis, and the hypothesis would be a because. Okay, so generally hypotheses have methods in them, mechanisms in them. Not my car is not running is not a hypothesis, that's an observation. An explanation for the observation is what the hypothesis is. The car stopped running because the battery died. So that has a mechanism. Why did it happen? And a good hypothesis is a testable explanation. So I already explained how we could test the battery dying, but how do we test that you ran out of fuel? And the issue is that you can't really see in the fuel tank, and you can't really weigh the car to find out if it's not as heavy. So one way you'd have to test it would be a full experiment. You would say, if I add fuel to the car, if it's true that the car is out of fuel, then adding fuel will make it start. That is the basis of, that's the setup for your experiment. You would go, get fuel, bring it back, pour it into your car, and hopefully your car will start. Now, if not, obviously then something else is wrong, and your hypotheses have not been supported by the data. If your car is going and there's black smoke pouring out of your tailpipe, it's probably not your battery or fuel. So a prediction states what will happen when testing the hypothesis if the hypothesis is correct. If it's true the car is out of gas, then adding fuel will make it start. You can also have an alternate hypothesis, your null hypothesis. Nothing I can fix right now will fix my car. And if it's true that the car is broken beyond my repair, then it's neither the battery nor the fuel tank, and neither one of these will work. Okay. Now, hypotheses are what's called an informed guess. When we were creating these hypotheses, you definitely said, oh, I know. It's got to be the fuel tank. It's got to be the battery. But you wouldn't say, oh, I bet my key fob battery is dead. Well, then you still be able to start the car, though. And you wouldn't say, oh, I bet it's my windshield wiper fluid. Because you know the windshield wiper fluid doesn't do anything to start the car. Because you have some background information. And likewise, there's many things that could correlate but not cause. For instance, there's an old story about so car talk, long time ago. They used to do car talk with these two guys who would like laugh and help you solve your car problems. Someone explained that when they went in to get vanilla ice cream for the kids, they would drive to the store, get vanilla ice cream, come out, and the car wouldn't start. And the engine would flood. But when they would go in the store and they would pick out whatever the kids wanted to eat, they would bring the kids with them, and the kids would pick out what they wanted to eat, the car wouldn't stall or flood. And the answer was, it wasn't vanilla ice cream that caused it. This is the thing. It was correlation for the vanilla ice cream, because actually the true cause was that this was an old car that struggled to start and restart multiple times, and when it was restarted, when it was hot, it would stall out, and the engine would flood. But if you started it up after you'd let it sit for a half hour, which is about how long it took for the battling kids to choose the type of ice cream they wanted, then the car would start. So it was actually the time. So you see on the screen it says correlation is not causation. And that's a good story to implement it. But this is another good story, a story that's going on right now when we talk about vaccination. Many people have been pointing towards millions of different problems that are happening all over the world. Oh no, vaccination must be causing this. We never had any of these troubles before COVID vaccines or something. But this is one explanation for people who have been anti-vax for a long time. And for instance, California begins the MMR vaccination right here. The UK begins the MMR vaccination right here. And this is number of enrolled persons with autism. Whoa, autism rates are spiking. Must be the MMR vaccine. And so this was the thing. People are like, what could be causing all of this autism? It must be the vaccines. Look at the correlation. Well, this actually doesn't say anything about why MMR would have caused it. There's lots of speculation. Oh, it's the mercury-based amalgam or something. Actually, they took that out a while ago and didn't change anything about autism rates. So another person was like, I bet glyphosate. Glyphosate is a very common type of herbicide that's added to tons of corn and soy crops. We've been using more glyphosate over the years because of these glyphosate-resistant crops that we've developed. Well, look at this nice little graph, a bar graph that says autism at age 6, and it's nicely going up over the years. And then glyphosate, the 4-year totals. Something tells me that with all this bars carefully set out, and these 4-year totals, not the 3-year totals, not the 10-year totals, not the 1-year totals. It's a little weird, right? And also the dates are kind of off here, not quite the same. It fits nicely. But just because it fits nicely doesn't actually mean a lot. You can also do this with, organic sales. As organic food sales have gone up, so has autism. You could do this with sales of the iPhone. The cost of Tesla. The issue here is that just having a correlation means almost nothing. You actually have to have some sort of reason, explanation. You have to have a mechanism. There's no mechanism for any of these things to cause it. You could even say that Jim Carrey causes autism. Their correlation is really high. Jim Carrey movies causing autism. So the actual reason that autism rates are going up is none of the above. Autism has actually not been getting worse. Counterintuitively, autism rates have increased because we're better at diagnosing it. Because more people recognize the signs, because more physicians are trained to recognize the signs, and people on the autism spectrum are being identified. It used to be that only people who were extremely autistic, in the sense that they were heavily on the spectrum, they were nonverbal, they had difficulty communicating anything. Those are the people labeled with autism. I know people with autism. I've taught people with autism. My brother has autism. But they're all functional members of society, and they don't have those extreme issues. And they live reasonably normal lives. All of this to say that we've just been better at recognizing it. And we've been diagnosing milder cases. It's not that autism rates are going up. Autism recognition is going up. All right. So basic scientific method: make observations, ask questions, develop hypotheses, design experiment, make predictions, run experiments, analyze results. So hypothesis itself is a tentative statement. It is not completely random. It can be a null hypothesis, okay? So you can say drug X makes students smarter. But a null hypothesis would say drug X has no effect on student test scores in Bio 1130. The difference between these two is whether or not they're null. Whether or not you're looking for your hypothesis is that there is a specific directional effect, or whether or not you're saying you're trying to kind of disprove the null hypothesis. Now, that's going to come up when we start talking about statistics, okay? But let's practice. You know what? I'm wondering if I did this one wrong, actually. Okay. So one of the things that has in your PDF is to practice and make a hypothesis about what makes grass look green. And then you have to come up with an experiment. Now, you're not going to be tested on this specifically, but this is a good practice for understanding this. For instance, in the actual PDF of this, it describes, what makes grass look green, what makes the sky blue, and the little boy said, "Oh, well, I think it's painted." And said, "Well, how would you test your hypothesis?" Well, he said, "I'd climb a mountain and I'd look up and I'd look for paint." And this would test what caused it. Now, obviously it's wrong, but, maybe you look at the grass under a microscope and you expect to see little flecks of paint because someone's been painting the grass green. That's a way to test it, and you'd be easily proved wrong. But, if you were to test something like, you say chlorophyll makes it green, well, how would you even know that chlorophyll is actually the green-making thing? Well, one of the key ways is to maybe, say, take a lighter green plant and a darker green plant. And if chlorophyll is indeed the green maker, see if one of these plants has a higher concentration of chlorophyll, which is easily done through a variety of analyses. All right, I'm actually going to skip over these inductive versus deductive. I thought I had fixed this one. So one moment, I do believe I actually have the incorrect setup here. I think I was supposed to not do the detective one, because I wanted to move on to instead talking about the simutext lab. One moment, I'll be right back. Okay, I don't actually know if it paused or not because I was confused with what I was doing. But here we go. I apologize. I did have, I copied some slides, and that was my error. So here we go. So we want to now test our hypotheses. How do you set up an experiment test? Okay. So how many replicates do you have? What experimental variable? How to control the experiment? And we'll be going through all of these on Wednesday in our synchronous lab. How do we even set up our experiment, cultivated versus uncultivated plots? Okay. But for a good data that creates good experiment that creates good data, you need the following: a control group, same as the rest, no treatment. Okay. And this would be in the laboratory. Now, we're not going to be able to do that in the field, but a control group, okay? So you need something that's not changed at all. You're going to compare it. Replicates, multiple individual tests of one treatment, and a well-planned activity. Now, the activity that you do has to actually test your hypothesis. So in the past, when some of the students have done this activity, the activity of the of collecting data about cultivated and uncultivated green spaces in the DC area, they've given me a hypothesis like, well, we think the people are going to be using more pesticides or less pesticides. And I said, but wait a second. If you're talking about this, then collecting data about the biodiversity does not test that. So you actually have to do an activity that tests your hypotheses. And so make sure that the activity you're doing tests the hypothesis as well, okay? And a successful experiment must have a control and experimental group. There has to be a difference in variables there. And our field experiment, even though we're not controlling things necessarily, we are experimenting on them, okay? So the only difference between the two groups would be some sort of variable. And this is going to be, like, for ours, this is going to be cultivation, okay? Now, this is a factor that you manipulate or is different between the two locations. And then you have a prediction. What do we expect to happen in that specific experiment if the hypothesis is correct? So as an example I always give people is that one of my students said in a different class for agroecology that she was going to interview people about their opinion on GMOs. And I said, well, that's very interesting, thinking that she would have a useful hypothesis. Maybe she's going to figure out who likes GMOs and who doesn't and compare those people groups. I should have pressed her further on her hypothesis, because her hypothesis was actually that GMOs cause cancer. But all she was doing was asking people whether or not they thought that GMOs cause cancer. The idea is that you would need a lot of rats and long-term study systems to discover that. Her actual experiment did not test the hypothesis that she had. She was just speculating. So if you have a controlled experimental conditions, or at least have a clear difference between your plots, and it's repeated and repeatable, you have a well-designed experiment. So your actual assignment for this week, for this specific thing, is to save the simploids. It's a simutext activity. I'm going to show you guys how to get onto simutext. If you have trouble getting there, let me know. But the idea is that you'd follow along with your professor in the video, run through it yourself, and ask questions before you answer the graded questions. A variety of different things, okay? Let me show you how to get on there. We'll save it, because I just realized that I need to re-upload that. So let's go here. Simutext is something that you download from the internet, okay? And I will show you, there is a link that's available now. It's not the correct link currently, but I will make it the correct link. Okay. So here we go. Okay. So they're still working on getting the summer one set up. So I am going to instead go to experimental design and walk you through what I had before. I may have to switch my screen. So give me a moment to do that. I'll look at this display. I'm going to go to display 2. All right, that should be right. All right, so understanding experimental design. This is your activity. So you're going to be going through the similar things that I walked you through just now, the what makes a good experiment, how do you experiment, etc. And watch this little video. It's about a town that has these cute little simploids and it makes people happy, and they begin getting sick and dying. So you've been hired to figure out what's wrong with the simploids, okay? Watch the video. It is actually pretty important to understanding this. But they give you 2 options or 3 options for what could be causing it, okay? It could be pesticides. It could be climate change, increasing heat, or it could be a parasite, okay? So this walks you through how science works, etc. So you're going to get a total of 5 points for completing all of this. And what you have to do is you have to participate in both the ungraded, which has these little questions that pop up throughout, and you have to participate in the whole experiment, and also graded questions at the end, okay? So for instance, you have to figure out, is this a well-designed experiment? 2 of your friends are in a class, they got their exams back. 1 listened to classical music and got a high grade. The other listened to the non-standard playlist and scored poorly. So the classical music listening friend claims that this is evidence that his music got him a better grade. And so the issue here is that why should your friend not attribute that? Well, there's obviously a lot more variables. And so you would click on the actual answers. This will check your answer for you. As long as you answer it, no matter if you got it right or not, then you will get the points. You do have to answer all of these kind of questions. Okay, so just read through it. It talks about confounding variables. What would you call the group of people to listen to classical music? And so this is how to set up an actual experiment that would test it. Okay. And then what does your conclusion mean in the real world? Can you replicate it? Okay. What's the experimental unit? So it goes through all these pieces. This is very helpful to understanding how experiments work, and we will be working with some of these pieces tomorrow. All right. Then it talks about replication. Okay. In particular, it talks about this crossbill experiment, and you watch a little video about the crossbill. What are you looking at? Okay. So you have all these spine presence or absence, these birds, and they figure out how long is it going to take you to get in there. And what about the birds that have different types of beaks? Okay. So they're manipulating it, trying to figure out if the crossbills are able to remove things faster if they have spines. And so you click this bird, you see that difference between spines present and spines removed, able to get to the seeds slightly faster. Doesn't look like that significant. But if you look at everyone and you start adding them all together, oh wow, actually this is significantly faster. So the average foraging time is actually much more significant in terms of the seconds that it takes them to get to each seed. And you wouldn't have known that unless you looked at all the birds, because some of the birds are faster in between both. All right. And then you have this, what do your results mean? Okay, so I'm going to skip forward. So this is checking your understanding. Again, answer all these questions. They are not going to be graded at this point, but this helps you understand how to set up your experiment in the next pile. Okay, so hold on one moment. All right, save the simploids, okay? So again, please watch the video. People in town have several ideas might be sickening the simploids, parasites, a new herbicide, and changes in temperature, okay? So you can see that the simploid disease is going up, but again, they're not sure what's causing it. And so, so let's look at the shamworm infestations. They're going up. Average daily head temperature, that's going up. Sales of zapweeds, that's going up. There's not enough information. We don't actually know what's causing it, okay? So now it gives you this information here. And you can say that, okay, everywhere is the same hot temperature. But there's variability in the lawns, okay? Some lawns have 6 simploids but no dead simploids. So some lawns have no simploids at all, and some lawns have healthy simploids. So we look at the disease rate, we look at the death rate, okay? So some lawns actually have healthy simploids. So now we have this information that because there's variability, in sick, dead, and healthy. Actually, what this says to us is that it's probably not the temperature, because the temperature isn't varying between these lawns. Okay? And so now you have parasites or herbicides. So you start out with the hypothesis. It doesn't matter which one you begin with. You should do both of them to understand which one's right. But let's say we start with the herbicide. Okay, so record your hypothesis. Okay, and so you get these 8 experimental study plots, and each one of them is going to have a certain set of symploids and is going to have a certain set you're going to add zapweed, the herbicide, or you're going to add sham worms. Okay? So remember that we chose I'm going to figure out what I chose. The herbicide. Okay? So what we're going to do here is that we are going to be just showing, okay, so we want to have a small number of symploids, maybe 10. There's not a lot of symploids here, okay? You want to have a good amount of plants. So every symploid needs at least 1 plant, so let's say 30 plants is a nice healthy thing. And we are going to put, if we put nothing here, that'll be our control, okay? And then you'll be able to conduct the test, and you look at your control, and look, if there's no sham worms and there's no herbicide, they are actually all healthy. So this actually gives us some very limited information that likely something is causing them. They're not just randomly getting sick, okay? So one of the two things is, and then we can collect data, and this gives you all this information. There's no sick, so we can go conduct tests, and then you'd be able to run a week. Okay, so I'm going to vary about the amount of herbicide and nothing else across study plots. My control group will have no herbicide. That should be how you set up the herbicide one. Do the same thing for the sham worms, okay? And we'll look at just ones that die, but you can also just look at the number who are sick too. But you would predict that the variable would be higher in the experimental group compared to control, etc. Okay? And if your results turn out the way you predicted, it doesn't necessarily mean that your hypothesis is definitely true, but it will support it, okay? So you can never really prove a hypothesis, but it does support your data. Okay. So let's start testing, okay? And so you'd add a study plot. Remember that you want to have 5 control plots and 5 study plots. So your control plots, and you are going to keep the number of symploids the same, keep the number of plants the same, and so you'll have like control 1, control 2, control 3, okay? And then the herbicides, so, and then you're going to compare and do that, okay? You want to check your setup at the end because it's going to tell you whether or not you have the right number of study plots, okay? I'm not going to do that, but once you do run them, you would see it. Let me just actually go back real quick. I'm going to, this is control 1, and I'm just going to make this one the same. Put 40 plants, and I'm going to add herbicide, okay? And then let's just conduct the test. Okay, now they're both here. Okay, and run 1 week. Okay, and keep going. Keep going. Keep going. Now, if you look at them, you can actually see that even though there is blood toxicants in the ones, none of the symploids are dying. See if you find something different if you do the sham worms, okay? So this is the concept. You're setting it up. You're collecting data. You have to set them all up and collect data on all of them to actually get full credit for this, okay? So make sure you're finishing everything, okay? And then you're going to give this information, and you are going to conclude something about this. And then you'd run another experiment, okay? So you'd run the parasite one, or maybe a combination of both, but probably you should do them each independently find out. Okay? All right. And that's all. And then now you have this information, what should they do? And from this information, you should be able to get some guidelines for how to keep their symploids healthy. The next page, once you get to the end of this, press the next page and it's going to take you to graded questions. Okay? And it's just a list of questions that you go through and you'll get 2 points for finishing them all. Okay? 3 points for finishing the rest. All right, that's all that I have. I will be present again for most of these. You can watch this video at any time, and remember that these come up very fast. The lab exam for this one will be coming next Monday, which is in less than a week. So do make sure that you are paying attention to time frames. All right, have a great day.